Hi, welcome to the Unit 1.5 Foundations of Chemistry video. This video will focus on the second key question, analyzing matter. Just like with any video notes, make sure you annotate, and linked in this assignment as well will be an additional video which is optional in case you want to see more practice problem, whether now or later. All right, in this unit we have been looking at chemical reactions, and I just want to kind of take you through the process of what a chemist does when they're performing a chemical reaction. So first thing is they need to know how much of their reactants that they need, and they use stoichiometry for that. They also need to figure out which one of their reactants is their limiting reactant, so they can use that to figure out how much product they can make or their theoretical yield. Once a chemist has its product, chemists want to analyze the product because you never know, maybe a reaction goes wrong, and you want to make sure your product is pure and that you have what you think you have. And so one of the things that we do is we analyze our product using various techniques. One technique is elemental analysis, and the way that elemental analysis works is it tells us the percent of each element in a molecule by its mass. And here we just have an image of an elemental analysis machine. Okay, so let's say you're this chemist and you're like, is this my product? Well, you could take an elemental analysis, and what an elemental analysis will give you, you can use it to find the empirical formula. Now, that doesn't mean that it is your product exactly, but if it matches, then it's great. It's good evidence that you have what you think you have. So the process for an elemental analysis, you use it to get your mole ratios, which then can give you an empirical formula followed by your molecular formula, and then again you can use that to sort of support whether or not you have your product. Okay, so let's take a look at sort of the process before we go through some examples. Elemental analysis data will often look like this. It gives you the percentage by mass of each element. So here we have an example of what it would look like if we had an element or a molecule made up of carbon, hydrogens, and oxygen. And that's each element's percentage by mass. From these mass percentages, we can get their mole ratios. So let's say we do the work here, we find that that corresponds to a 3 to 6 to 2 mole ratio of carbon to hydrogen to oxygen. These mole ratios can then be plugged into an empirical formula, so C3H6O2. And if you know the molar mass of your unknown, you can use that to get the molecular formula, which is here. And there are other techniques like mass spectroscopy, etc., that will help you to get the molar mass. Okay, so empirical formula gets you your molecular formula, and once you have that, you can sort of match it up to a compound. Now, once again, it doesn't mean that just because you have this empirical formula, that molecular formula, that that's the only compound that it can go with. But again, this is good evidence to sort of support what you think you have, what you hope you have. All right, just want to show you what an elemental analysis report looks like. Again, these percentages, it's important to note they're percent by mass. So this is just sort of an example of what one looks like. So how do we do this process? How do we go from the percentages to mole ratios to empirical formula to molecular formula? Like, how do we do all that? This is a multi-step process, and one useful technique is to memorize this wonderful poem that my high school chemistry teacher taught me that I've always remembered. The poem is percent to mass, mass to mole, divide by small, times to whole. And maybe you're not, that seems a little bit dry to you, so you can sort of jazz it up, you know. So you can maybe make it a hip hop beat, percent to mass, mass to mole, divide by small, times to a whole, hey. All right, sorry, it's a bit corny, but I'm from the 90s, and so that sort of will fit more of my style. All right, so here you have this poem, and these are the processes we're going to use to sort of get our empirical formula. Let's look at this example problem. According to elemental analysis, your unknown hydrocarbon is composed of the following elements: 48.6% carbon, 8.16% hydrogen, and 43.2% oxygen by mass. What is the empirical formula of your unknown? All right, we're going to do the work on, I'm going to do it on a separate slide, and you're going to make sure you copy down the work on a separate sheet of paper or on your note packet. All right, so here's the key information from here is the percentages of carbon to hydrogen and oxygen, their mass percents. And the best way of doing this is sort of setting up this table here, where I take the parts of the poem, percent to mass, mass to moles, divide by small, times the whole, and I make a column for each one. And in each row, I have the elements. So take a moment to set up your table. All right, so I'm given the percentage of each item. To go from percent to mass, all I do is change the percent to grams. And the reason why that works is because if you assume that you have a 100 gram sample, then if you have a 100 gram sample, then 48.6% of 100 grams is to 48.6 grams. So basically you can just assume, make that assumption and change all percentages into grams. Now let's go from mass to moles. For that, it's real simple. We're going to use the moles equals mass over molar mass equation. And so I take all of these masses that I have now and I divide it by the molar mass or atomic weights that you can get from the periodic table. So for carbon, it takes 48.6 grams and divided by 12.01 grams per mole. And again, this number comes from the periodic table. And that gives me 4.05 moles of carbon. I do the same thing for hydrogen, the 8.16 grams of hydrogen divided by its atomic mass, and I get its moles, and I do the same thing for oxygen as well. So now I have three different moles here, one for carbon, one for hydrogen, one for oxygen. The next step in the poem is divide by small. What does that mean? We want to get the mole ratio. So in order to get that, we need to divide each of the mole values by the smallest moles. That way it will give us their smallest mole ratios. So I look for the mole that's the smallest, and it's oxygen. All right, so there's only 2.70 moles of that, and everything else is higher. So I'm going to divide all the other moles by that, including oxygen itself. So 4.05 moles of carbon divided by the 2.70 moles gives me 1.5. I do the same thing with the 8.10 moles of hydrogen and get 3. And then I do the same thing with the oxygen. So you must also do it with itself. 2.7 divided by 2.7 gives you 1. Now I have my mole ratios, but notice that one of them is a decimal. So whenever you have a situation where you have a decimal, you have to multiply until you get your whole number. And you want to multiply by the smallest number possible to give every value here a whole number. So taking a look at this, it's super helpful to convert from decimals to fractions in your mind. When I see 0.5, I think of 1 over 2 or 1/2. The smallest number I can multiply 1/2 by in order to get it to become a whole number is its reciprocal, which is 2 over 1 or just 2. So that means I need to multiply this by 2. And whatever I do to that value, I have to do to all the other mole ratio values. So the last step here would be multiplying everything by 2, and then that would give me 3, 6, and 2 as my mole ratios of carbon to hydrogen to oxygen. Cool, so now I know how many my mole ratios. I can now go ahead and plug that into my empirical formula. So 3 moles of carbon, see carbon here, that second row. Hydrogen with 6, and then oxygen has 2, and I just plug that into an empirical formula. All right, so now that you've seen this whole process, percent to mass, mass to moles, divide by small, times the whole, it's your turn to do it with this CFU. So take a moment, read through the CFU, and then I want you to set it up similar to the way that you saw me set it up before with a table or some sort of structure where you have spaces for each piece of your work, and then when you press play again, the answer will be revealed. Okay, so let's see that process here. Once again, percent to mass, mass to mole, divide by small, times the whole. So we're going to convert all of our percents into mass just by changing the percent to grams. Once we have our mass, we plug it into our moles equal mass over molar mass equation to get the moles for each element. Once we have the moles of each element, we're going to divide by the smallest value to get our mole ratios. And in this case, carbon and oxygen both have the smallest value for moles. So when we do the math out, we get the mole ratio 1 for carbon and oxygen and 1.33 for hydrogen. I notice I have a decimal here, and so I have to do the last step. If there were no decimals, you wouldn't have to do the last step. This is where you would stop. But since we do have a decimal, 1.33, I need to figure out what's the smallest number I can multiply it by to get whole numbers. Well, again, I like to convert this to fraction. When I see 0.33, I think of 1/3, which is like 0.333333. So I think of, well, if this is 1 and 1/3, this value here, what's the smallest number I can multiply it by? It'll be the reciprocal of 1/3, which is 3/1 or 3. So I'm going to multiply each of these values by 3, and that gives me the whole number molar ratios. I plug those into my empirical formula, and I get the empirical formula C3H4O3. Okay, now we're going to do use this information to get the molar mass of an unknown. And we're going to use the information from example problem 1. Before we could go on, please make this correction here. The molar mass of the unknown, it should be 148 grams per mole, not 108 grams per mole. So please change that 0 to a 4. All right, so from this information, knowing the molar mass of the unknown, we want to know what the chemical formula is. Now, before we move on, let's just take a quick recap of molecular formula versus empirical formula. So the molecular formula is the chemical formula for the entire molecule, where the empirical formula is the chemical formula with the smallest whole number ratios. So how will we go from a molecular formula to an empirical formula? Remember, we just looked for a least common factor to divide each of the subscripts by. So in this example here, the least common factor is 2. So we divide everything by 2. And for the second example, the least common factor here is 6. So we divide everything, all the subscript, by 6. And then that will give us the empirical formula, which is the same for both of these, which is CH. So in order to do the reverse, which is going from the empirical formula to the molecular formula, I need to figure out what that least common factor is. And the way that we do that is we're going to use the molar masses of the molecular formula and divide it by the molar mass of the empirical formula, which should make sense because if you take a look at the compare the molar mass of the empirical formula to the molecular formula, for C2H2, the molar mass of the molecular formula here is twice that of the empirical formula, and for C6H6, it's 6 times that of the empirical formula. So by dividing these two molar masses, I can get the least common factor, which is what I want and what I need to go from the empirical formula to the molecular formula. All right, let's see that with that example problem. So what I need here is the molar mass of the molecular formula and that of the empirical formula. For the molecular formula, they gave me that in the problem. They tell me that it's 148 grams per mole because that's the mass of the actual unknown. And now I just need to use the periodic table and my empirical formula to get the molar mass of the empirical formula. So that will be 3 times 12.01 plus 6 times 1.008 plus 2 times 15.99. You add those together and that will give you the molar mass of the empirical formula. And when I take my two molar masses and I divide 148 by 74.06, I get a value of 2. That means my least common factor is 2. So that means the molecular formula, to go from the empirical formula to the molecular formula, I need to multiply all of these subscripts by 2. And I do that and I get my molecular formula to be C6H12O4. All right, you've seen how we do with that example problem. It's your turn with the CFU. So you're going to read through the CFU and pause the video when you are ready, and you'll press play and the answer will be revealed. One quick note, we are using the information from CFU 1, so you may need to go back to that. All right, pause the video now and the answer will be revealed when you are ready. Okay, so we are using the empirical formula from CFU 1, which is C3H4O3. This is the equation that we're using. So the molar mass of the molecular formula is given to us, 176.12. And for the empirical formula, again, I just use a periodic table to find that out. And what I get in that case is the molar mass of the empirical formula is 88.03. I divide that into the molar mass of the molecular formula, and it just so happens that in this CFU, the least common factor is 2, just like in the previous example. It's not always 2, but it's just a coincidence. Okay, cool. So I got my least common factor. I can go ahead now and multiply these subscripts by that least common factor. And then that will give me my molecular formula, which will be C6H8O6. All right, folks, hope you found this video helpful. If you need more practice, there's an additional video linked in the assignment. All right, have a quality day.